G'day viewers. In this segment I'll introduce quality of service. So here's a protocol layered diagram to tell us where we are in the course, and we've now already covered everything from the physical layer up to the application layer. We're now going to talk about quality of service, and that's a topic that, as you can see here, spans several layers. It goes all the way from the application layer, because the application needs to be able to tell the network what it needs, down to the network layer, because the network is the layer which ultimately provides different kinds of network service to applications. So the topic of quality of service relates to the kind or type or level of service that a different application or user on behalf of that application receives from the network. Now we're going to end up defining that in a way which depends on the particular application. So we might be talking about whether we want a certain amount of bandwidth, high or low bandwidth from the network. Or an application might actually not really care about bandwidth very much at all. It might care more about low levels of delay and loss, as we'll see in an example in just a moment from the network. So we'll look at this topic, and I also want to flag here this point, that quality of service is an important issue for the future of the internet. In the internet today, we really don't have much in the way of quality of service support. We get what's called the best effort service from the FIFO routers in the network. In the future, we're likely to see improvement in terms of quality of service, with various mechanisms being deployed to provide stronger levels of quality of service, higher guarantees of quality of service for different applications. But a lot of that's in the future, and we're just at the beginning of that. So we'll look at what happens today and where things might head in the future. So first of all, I should talk about the internet today, and that's this best effort service. So the term best effort, that's what you get from the internet today when all of the routers are FIFO routers. And here's a picture of a router down at the bottom of this slide. And if you recall, the way they work is packets might come in on different input lines from different places into the router, and they queue up in a queue to go out a particular output link wherever the routing sends them. And it might just be the case that for this particular output link I've indicated, a queue builds up, just because a lot of traffic wants to go out that link. This leads to congestion, and the packets that go out this queue are delayed because of the excess queuing, and if the queue overflows, some of them are lost. So the applications here compete for bandwidth, and the queuing can add the delay and the loss, just depending on the traffic patterns and what the apps want to send. The best effort service provided by these routers will do its best to deliver all of the packets, but there's no guarantee of the particular amount of bandwidth, delay, or loss you'll get. Often it might be fine, sometimes it might not. So that's the internet we have today. But sometimes best effort just isn't enough. You might want different kinds of performance guarantees if you needed a minimum amount of bandwidth to make the application work, and so forth. So that's what quality of service will try and provide. Now, we've got to be a little careful though. There are some things we can't do because they're just impossible. We can't guarantee more bandwidth than the network can actually provide, or lower delay than it takes for messages to actually cross the network. So we can't do the impossible. However, what we can do is control how the bandwidth is allocated to different applications, and because we control all the way the bandwidth's allocated, we'll also control properties that come from that, such as the variation in delay and the loss. And by changing the way the bandwidth is allocated, we can come up with an allocation which is maybe a little better, and we'll do a better job at giving different applications what they most want from the network. Well, let's see an example of that, how that might work. So for my example here, I'm imagining that you're at home. Here's your home setting on the left, and you're talking to the rest of the internet across your access link. This access link is going to be the bottleneck. It's the limited bandwidth portion of the network, and so queues will build up on the routers on either side of this bottleneck. Now at home you're running two applications, and you're running them both at the same time. Skype, and Skype, this will just be a voice over IP call, so not a lot of bandwidth, and BitTorrent. And we're running these at the same time, but note that we want really different things for the different applications. Skype cares most about getting low latency communications and probably low levels of loss. This is so your Skype call quality will sound good. Your call won't sound choppy or broken up. And BitTorrent, on the other hand, doesn't really care about a bit of variation in delay. BitTorrent wants to grab as much bandwidth as it can. A bit of delay or loss, it's just fine. It's trying to do a bulk transfer, which is why it needs all this bandwidth. Okay, so let's see what happens when we run these two applications with FIFO routers. Well, the two applications are going to send packets. In this direction, they'll build up this queue here, and in this direction, they'll build up this queue here as packets queue to get onto the bottleneck link over the access link here. Now, the two applications will compete over the link, and as they compete and the Skype sends a lot of traffic, queue is going to build up. Well, what will happen when queues build up? Nothing particularly good. In fact, as queues build up, we'll see increased levels of packet delay and we'll see some levels of packet loss. This means that Skype is a little bit out of luck. The Skype call quality is going to fall because of the interference caused by BitTorrent. And if you've ever tried running a Skype call at home while running something like BitTorrent, you know what I mean. It can be pretty bad. If you're trying to Skype or even watch a bit of video and while you're doing something else, it can really interfere with your application. The quality goes way down the drain even if you are getting some bandwidth. BitTorrent, on the other hand, will be mostly unaffected. Skype will use a little bit of bandwidth, but it wasn't using much, so BitTorrent is actually doing pretty well. But Skype's not. So what could we do? Well, there's actually not too much we can do with what we've seen so far. About all we could do, since we've just seen routers and links and other things, is we could add another link to the network. We could somehow split the access link into two different links, and for an apples to apples comparison, we'll say that each of them has half of the bandwidth. Could be some other fraction, but let's just say a half. And we could change the routing so that the BitTorrent application goes over one of the access links and Skype goes over the other access link. This would be a fair bit of bother to go to, but let's just see if it's going to do anything to solve our problem. Okay, well, now the Skype packets, they're queuing here. There's very few of them, so they basically go on the link right away. And the result is that the Skype call quality is good. Skype sees low levels of delay and low levels of loss. It's happy. Good call, we're happy. On the other hand, what about BitTorrent? Well, BitTorrent will work well and saturate this link here, but it's basically lost half of the bandwidth available to it. So BitTorrent is not doing nearly as well as it did. And we've come up with a fairly complicated network just to try and fix one of these, and we really haven't fixed the whole problem. Could we do better? Well, I'm glad you asked. In fact, we can do better. Here is a brilliant idea that we might try, sort of. And quality of service will take us towards some of these things. Here's the idea. Let's just use the one access link and the routers adjacent to the access link here. These are the access routers. We're going to modify them so that we're going to tag the Skype packets with a VIP tag, very important packet, I guess, and we'll modify the routers here to give Skype packets priority on the link. So you can see here I've shown that the BitTorrent packets are queued, they go in a queue, but if a Skype packet comes, it just goes straight onto the link. Well, and to do this, we have to change the router. So we're changing the way a router works to do this. What's going to happen if we do this? Well, guess what? Now we're happy for both of the applications. We get a high call quality for Skype because the Skype packets see low delay and low loss. And at the same time, we get a high throughput for BitTorrent because BitTorrent gets all of the bandwidth that's left over that Skype's not using. So in fact, if Skype is not running concurrently with BitTorrent, BitTorrent would get all of the bandwidth. And that would never happen if we divided our access link, for instance. So BitTorrent is getting as much throughput as it can. The point is that both of these applications win. And we can do this because they were after slightly different qualities. One cared more about delay and one cared more about throughput. So we rearranged what the network was doing to better support both of those applications. That's pretty cool. And that's an example of what you can get from quality of service. So backing up to quality of service from that example, what quality of service is all about is allocating the bandwidth in different ways than we would get with FIFO routers in a way that's going to improve the application performance for the various applications. We might, for instance, want to guarantee a certain level of bandwidth to an application if it needed that much bandwidth to run, like for instance streaming video, you might have a minimum rate, or we might care about delay as we've just seen. And it may be the case that you can do a better job of satisfying multiple apps with quality of service mechanisms. You might be able to make all of them happier than they would otherwise be. That's pretty good. And I want to note here that I use priority as a simple motivating example. That's not used in networks, really. Networks use mechanisms which are slightly more general and generally more useful. And we will explore those ideas as we look at quality of service. And I'm thinking of things like fair queuing and weighted fair queuing. We'll get to what that means later. Okay, but one point I've got to make here is that to provide quality of service, what quality of service actually is sort of depends on applications. So we need to know what it is that applications require of the network Do they care more about getting a high bandwidth, a low delay, a low variation in delay, low loss, or maybe something else entirely? We need to know before the network can possibly provide it. This table here just gives us a way of thinking. I've shown some example applications and the different kinds of things they might want of the network to get you thinking about it. So the network qualities we're looking at are bandwidth, delay. Jitter here is maybe a new one. I'm not sure if I've mentioned this. Jitter just means variation in delay. So it's not the absolute delay, which just, there's a minimum delay for the signal to travel down the wire. It's the variation in delay that's going to come from things like queuing in the network or taking different routes. And there's also loss, because we might get packet loss. Now, this table lists the stringency with which an application requires any of these network characteristics. A high stringency, so high in this table, means you have a strict need for the quantity. For bandwidth, a high stringency means you want a lot of bandwidth. For delay, a high stringency means you want low delay and low loss, right? The more difficult one to provide. And we can see here that different applications really do have different needs in terms of these qualities, which is what makes quality of service interesting, of course. Email, for instance, doesn't really need much of anything. It needs some bandwidth and a bit of delay and loss, and eventually your mail will get there and you'll be happy. File sharing, well, it doesn't have strict performance guarantees, but it does want a lot of bandwidth, so you can get your file there in a reasonable time. Other things may have different qualities. I've listed here audio on demand, like a podcast or so forth, benefits from a highly stringent control over jitter. So you want low variation in delay. That's so you don't get fades, and we can use techniques so that when we start streaming, you get a nice continuous smooth playback. On the other hand, things like telephony, which is interactive, it's not a podcast through two people talking to one another, not only do you want fairly low variation in delay, but you also want fairly low delay because we have a highly stringent requirement on the delay characteristic. And video conferencing, well, much like telephony, but I've said here that we have a highly stringent need for bandwidth because video is just going to require more bandwidth out of the network. So the point from this table, the takeaway is different applications have different needs, and you can think a little from the application to understand what they are. Great, well, we're going to dive into quality of service in some of the coming lectures. Before we do that and I give you a table of contents, I want to tell you about one caveat. The caveat here is that quality of service only matters when there's actually a bottleneck in the network somewhere. If there's no bottleneck, then there's no queuing and there's no loss, and everyone's getting as good a performance as they can from the network. There's really no opportunity here to improve the performance characteristics that the applications are seeing. Well, this does actually lead to one possible approach to quality of service, or maybe I should say an alternative to quality of service. And that alternative is to, instead of building quality of service smarts into the network, simply build a network with heaps of capacity, so you'll never have any bottlenecks. This is a simple alternative, and you can do it and you can try and do it. In fact, that's what a lot of the internet has been based on at different times. But while it's a simple alternative to quality of service, and it works, if you can get it going in the early days, it's actually not a terribly effective approach for a couple of reasons. The first is that it's not really very cost effective. There's nearly always some bottlenecks somewhere in the internet. Maybe it's not in the ISPs, but it's in the backbone links and so forth. In that case, it would cost a lot of money to build a network that really had no bottlenecks. Even for an ISP, providing a network to ensure that you have no bottlenecks inside it can be quite an expensive proposition. So if we can make quality of service work, we may end up with a cheaper network. So it can be not cost effective. And the other difficulty is that over-provisioning gives you no guarantee. It might work on a sunny day when you have your normal traffic levels, but under an attack scenario or growth that maybe you didn't predict, well, things might not behave so well. You have no guarantee that applications will continue to receive the performance they need to run in the way users expect. That's why we'll talk about quality of service mechanisms and see how to actually add some of that to the network. We're going to go over several topics. I've talked about the different application requirements that they might have for different kinds of qualities. That's what we mean by quality of service, the different requirements for applications. Next, I'm going to talk about, in the coming modules, different ways of handling applications that you might think would need quality of service that we handle in the internet today. Real-time applications like voice over IP, and also streaming media applications like playing video over the internet. We clearly do them in the internet today. Well, how do they work and how well do they run? And after we cover that, I'm going to go down this progression talking about different mechanisms we can add to the internet to provide stronger guarantees of quality of service. These range from mechanisms called fair queuing that we'll get to and ways of shaping traffic to architectures for providing quality of service. Differentiated services is one architecture, and the strongest forms of quality of service we'll see, which are not deployed today, are providing rate and delay guarantees to individual applications. Okay, so on to quality of service.